What if I told you that in the quantum world, cause and effect might not always be a real, fixed thing? Not we don't know which happened first. But something even stranger, the order itself isn't decided until you measure it. Today we're going to explore an idea that sounds like science fiction, but comes from real experiments. The quantum switch, a setup where two operations can happen in a superposition of A, then B, and B, then A. And then we'll zoom out to the big question that makes physicists lose sleep in the best way. If causal order can become fuzzy, could space-time itself be something that emerges from deeper information like physics? Welcome to MindSpark, Science Now. Let's light the fuse. If you're a human on Earth, your brain is built on a simple rule. First this, then that. Cause, then effect. Even your memories are filed in order. Breakfast before lunch, yesterday before today. Physics has always leaned on this too. In classical physics, events have an order. Even in Einstein's relativity, where different observers can disagree about simultaneous, there's still a structure. Something inside a light cone can influence you. Something outside can't. Causality is the scaffolding that keeps reality from collapsing into nonsense. So why mess with it? Because if we want to unify quantum mechanics, the rules of tiny things, with gravity, the rules of space-time, something has to give. And one candidate for the thing that bends is the assumption that causal order is always definite. Let's define it in the simplest way. Imagine two boxes. Box A does something to a signal, maybe rotates light polarization. Box B does something else, maybe adds a phase shift. In everyday life, you must choose A then B or B then A. And that choice matters. Some operations don't commute, meaning the final result depends on the order. So far normal. Now here's the twist. Quantum physics allows superposition. A system can be in multiple states at once, as long as you haven't measured it. Most people hear superposition and think a particle is here and there. But you can also put something more abstract into superposition, like a path, and in certain setups, even the order of events along that path. That's where the quantum switch comes in. Picture a traveler approaching two doors, A and B. Classically, you pick a route, A then B or B then A. But in a quantum switch, the route choice is controlled by a quantum system, often called a control qubit. If the control is in state 0, the traveler goes through A, then B. If the control is in state 1, the traveler goes through B, then A. And if the control is in superposition of 0 and 1, then the traveler goes through both orders at once, in a very precise quantum mechanical sense. This isn't just a philosophical claim. In real experiments, researchers use photons, particles of light, and optical devices that implement operations A and B. By preparing and measuring the control and the photon, they can demonstrate interference patterns that only make sense if the order was genuinely in superposition. The phrase you'll hear is indefinite causal order. Not unknown order, indefinite order. And that's a massive conceptual shift. Okay, pause, because this is where the internet goes wild. This does not mean you can send messages to the past, you can build an instant time machine. Reality is anything you want. Indefinite causal order isn't magic. It's a carefully engineered quantum resource inside a controlled experiment. Think of it like this. A quantum switch doesn't let you violate physics. It shows that physics allows a broader category of processes than we're used to thinking about. It's like discovering that roads can sometimes behave like waves. You still travel within the rules, your intuition just has to expand. So why care beyond the mind-blown factor? Because indefinite causal order can be useful. Some studies show that placing operations in a superposition of orders can offer advantages, like improved communication through noisy channels or more efficient ways to query black box operations in quantum computing tasks. In plain language, if you're trying to transmit information through a messy environment, sometimes a quantum switch gives you a new lever, because the order of operations becomes part of the computation. This is one reason the topic matters. It's not only deep metaphysics, it's also potential technology. But now let's zoom out, because the real spark is what it hints at. Here's the big question. If even the order of events can become quantum, then maybe space-time, our stage of space and time, might not be fundamental either. Over the past couple decades, a powerful idea has grown in theoretical physics. Spacetime may emerge from quantum information, especially from entanglement. Entanglement is that weird quantum link where two systems share a joint state. It's not just correlation, it's deeper. Measuring one system helps define the other, even if they're separated. Now imagine a huge web of entanglement, like a cosmic fabric of information. Some theorists argue that the geometry of spacetime might reflect the structure of that entanglement network. One famous line of thought, in simplified form, is more entanglement, closer in spacetime, less entanglement, farther. In certain holographic theories like ADS/CFT, the math connects geometry to entanglement in a remarkably concrete way. There's a deep relationship between the amount of entanglement in one description and the shape of space in another. Even if you've never heard the equations, the intuition is stunning. Maybe space isn't a container things sit inside. Maybe space is what relationships look like when viewed at large scale. Now let's bring in the most dramatic laboratory in the universe, black holes. For decades, there's been a paradox. Quantum theory says information can't be destroyed, but black holes, through Hawking radiation, seem to evaporate in a way that might erase information. That would be a catastrophe for physics. In recent years, something remarkable happened. New theoretical tools suggested a way to recover the expected behavior, often discussed through the idea of the page curve, which is a predicted pattern of how information should leak out of an evaporating black hole. The modern story, told carefully, goes like this. When you calculate the entropy of radiation in certain models, you must include subtle contributions, often nicknamed islands or replica wormholes, and when you do, the page curve comes out right. Translation. The math starts agreeing again with the idea that information isn't lost. Is it proven for real astrophysical black holes? Not in a final, experimental sense, but it's a major conceptual milestone. Quantum information methods are reshaping our understanding of gravity. And that loops back to our theme, if gravity and spacetime are deeply tied to information, then strange quantum processes, like indefinite causal order, might be glimpses of the deeper machinery. So what should we watch for next? Cleaner, more decisive experiments. Quantum switch and related setups are real, but the frontier is stronger tests, more device-independent demonstrations, better noise handling, and clearer separation from alternative explanations. Practical quantum advantages. If indefinite causal order becomes a standard tool, like entanglement is today, you'll see it appear in more applied quantum protocols. Bridges to quantum gravity. This is the most speculative but most exciting. Frameworks that treat causal structure as quantum and then recover classical spacetime as an emergent approximation. If such models start making testable predictions, even subtle ones, that's when the story becomes truly explosive. Let's land this with three takeaways. First, causality is not as untouchable as your brain thinks it is. Quantum physics allows processes where order is not fixed. Second, this isn't mysticism, it's a real experimentally studied resource. The quantum switch shows measurable effects that depend on indefinite order. Third, the biggest story might be what this hints about reality's foundations. Space-time and causality could be emergent, arising from deeper quantum information structure. And if that's true, then the universe isn't a stage where information plays. The universe might be a story written in information, and space and time are how that story looks when you zoom out. If you enjoyed this kind of frontier science where real experiments collide with deep questions, subscribe to MindSpark Science Now. And in the next episode, we can go even deeper. Is time itself an illusion created by entropy and information flow? Because if causal order can blur, the next question is obvious. What is time really? Until next time, stay curious and keep your mind sparking.